Okay, so welcome everybody. So last lecture we had ended with a discussion of cylindrical coordinates. And so cylindrical coordinates, as we saw, was really just polar coordinates, like in the xy plane, with a z added, right? So this was r theta z is how we described these cylindrical coordinates. And so imagining um, this picture, so I had a nice picture from last time, maybe I'll replicate it real quick. So to describe a point xyz in space, if we projected this point down to the corresponding point xy0 on the xy plane. All right, so we're essentially ignoring the z component here by zeroing it out. So if we do that, then in the xy plane we can apply what we know about polar coordinates to say, well, this xy point can be described, of course, as having some radius from, that is, some distance from the origin in the xy plane that we called r in polar coordinates. And this angular amount measured from the positive x-axis we're calling theta. And so this point in polar coordinates is r theta, and there was no z coordinate, so we just call this 0 here. So then what is xyz in polar coordinates in this system? Well, it's simply the polar coordinates r theta with the height z tacked on. Okay, and r and theta are related to x and y exactly as they're related to x and y in polar coordinates. So x is r cosine theta, y is r sine theta. Okay, so that's one direction. The other direction, so r is the square root of x squared plus y squared. A lot of times I write this without the radical, so I write this expression as r squared is equal to x squared plus y squared. It's the same thing. It's equivalent here. And here, if I divide y by x, the r's cancel. I get sine theta over cosine theta. So tan theta is y over x. Or another way of writing this is to say that theta is arctan of y over x. Okay. So here is my total description going from polar coordinates to rectangular coordinates and back. So one takes you in one direction, the other takes you in the opposite direction. Here's my complete description of cylindrical coordinates. Okay, well, you might say that, well, this is polar coordinates, and it is, but I take the polar coordinates and I slap the z height on, and now I'm dealing with cylindrical coordinates. Okay, and as we saw last time, cylindrical coordinates can be used to describe several of these objects that we might otherwise describe in rectangular coordinates. But it's really, like, where it shines is when the region in question that you're integrating over is some cylindrical region, or some part of a cylinder is involved in the formation of this region. Okay, because as we saw, a cylinder in cylindrical coordinates is given by the expression r is equal to a for some positive real number a. This specifies a cylinder, right? Okay, so if you're confused by this, you can refer to the previous lecture, what I did at the very end. I made a table of surfaces, a cylinder, sphere, a double cone, circular paraboloid, and I listed out that table what each of those things were in both rectangular and cylindrical coordinates. So if you're confused by that, have a look at the last lecture video. Okay, so suppose that we have the task of computing a triple integral over some region D of some function xyz dv. Okay, and let's say for whatever reason I'm led to believe that this region D would be more nicely described in terms of cylindrical coordinates. Okay, so first off, if this region D can be described as a region bounded above and below by functions of x and y, so say we have a region D, and it is in the usual style. There's a lower function, big F sub 1 of xy, and an upper function, big F sub 2 of xy for all xy in some region R. All right. Then this triple integral, this is just my definition of the triple integral, is the double integral over R of the integral from big F sub 1 xy to big F sub 2 of xy of little f xyz dz, and then this outer double integral is dA. All right, this is just my definition of a triple integral, right? So how can I apply cylindrical coordinates here? Well, because in cylindrical coordinates, the z coordinate is unchanged, that would lead me to believe that this inner integral is unchanged in some sense, so we'll see exactly what goes on here, and that this outer double integral then is changed in a way that's similar to how the polar coordinates integral is changed. Okay, so remember when we were doing double integrals, switching to polar coordinates allowed us to do double integrals that were maybe a little trickier if the region we're integrating over was nicer in polar coordinates. So let's see how this works for triple integrals in cylindrical coordinates. So we have the following fact. So this is how I compute triple integrals in cylindrical coordinates. How do I go about doing this? So let D be the region as I was talking about like 1 minute ago. So let D be the solid region bounded, we'll say, between the graphs of big F sub 1 and big F sub 2 on some region R, okay, where R is described in polar coordinates. So again, going back to what I said, the idea here is that my inner integral isn't really changed because I don't change the z going from rectangular coordinates to cylindrical coordinates. And then this R is going to be recast as a region expressed in polar coordinates, right? So between the polar graphs of some functions. So where R is the region, so is the planar region between the polar graphs of H1 and H2 on the closed interval alpha beta, where, remember, these are angular values, so we want the difference between beta and alpha to be between 0 and 2 pi so that they make sense as angles. And these functions of theta are bounded below by 0. This just allows, or I should say disallows, stupid stuff from happening. So these two polar graphs are bounded in this way for alpha less than, or for theta in this interval, this closed interval from alpha to beta. Okay. So if little f is continuous on D, then this triple integral over D of little f of xyz dv is equal to the integral from alpha to beta. All right, we're following polar coordinates now for the first double integral. The integral from h sub 1 of theta to h sub 2 of theta. The integral from big F sub 1 to big F sub 2. Now I'm going to think here for a second, right? You might be tempted to immediately write xy here, but you know that that is not going to be right because we are switching to cylindrical coordinates, or specifically for this region R, we're switching to polar coordinates for R, meaning that we're replacing any instances of x and y with how they show up in cylindrical coordinates in terms of r and theta. And so this is big F sub 1 of xy, but x is r cosine theta, and y is r sine theta. So for every instance of x, I plug in r cosine theta. For every instance of y, I plug in r sine theta. And I do the same thing in this upper limit of integration. Right? And I do the same thing in my integrand function. So this is little f of r cosine theta, r sine theta. For z, I don't have to replace anything because z remains as itself in cylindrical coordinates. Now you may say, in polar coordinates, there was an extra thing here before I could be done. There was an extra factor, right? There's an extra factor of r. Well, does the same thing happen here? Yes. What is the extra factor? It's also r. dz, dr, d theta. Okay. So this is my formulation for how polar coordinates work. Okay. Or sorry, cylindrical coordinates work for triple integrals. Now, as before, when we first did polar coordinates for double integrals, I want to draw your attention to this extra term. This extra term always shows up like this, in the exact same way that it did for polar coordinates. In fact, the reason this is the same factor that shows up as in polar coordinates, as you might have guessed, is because of how intimately related cylindrical coordinates are to polar coordinates. Literally, cylindrical coordinates are just polar coordinates with a z tacked on. Right? So this shouldn't be that surprising that we would get this factor showing up the same way. Again, we will see exactly where this comes from and what it is later. Okay, so when we investigate what's called the change of variables formula, we will see exactly how this arises. Okay, and so this is how this works. Okay, so now let's look at a couple of examples to see how we apply this. So let's consider the following. All right, so let's pick just a nice solid first example here. So let D be the solid region bounded above by the plane, which is y plus z is equal to 4, below by the xy plane, which of course is z equals 0, and on the sides by the cylinder x squared plus y squared is equal to 16. Okay. Now evaluate the triple integral over d of the square root of x squared plus y squared dv. Okay, so a couple of things to note. If you are confused about why this expression describes a cylinder, refer to the end of the previous lecture. Okay, so you might look at this and say that describes a circle, not a cylinder, right? In the xy plane, this describes a circle, right? In fact, viewed as viewed as its cylinder, the circle it describes is exactly the cross-section formed by intersecting that cylinder with the xy plane, right? But this describes a cylinder in space, right? So think of the collection of all points, x, y, z, satisfying this. This is going to give you an entire infinite cylinder up and down the z-axis, right? The z-axis is going to be the central axis for this cylinder. This is a cylinder of radius 4, right? So x squared plus y squared is equal to 4 squared. Okay, so notice cylindrical coordinates they weren't explicitly mentioned in this example. This is how these questions are going to be. When I give you an exam on these topics, I'm basically never going to tell you what coordinate change you should use. Okay, and so it's going to be up to you to figure out what best fits the situation. And so in this case, we're talking about a region that involves a cylinder. Okay, and so we guess that cylindrical coordinates is going to work just fine. All right, so to see this, we first need to carefully describe D. And so D is a region where Z is bounded between some functions. So it's bounded below by the xy plane. That is the function Z equals 0. So that's my bottom. What's the top here? Z is bounded above by this plane y plus Z is equal to 4, which is really Z is equal to 4 minus y, right? And so this is what my domain is bounded below and above by on some domain R. Now let's figure out what R is. Maybe I should try to draw this picture here. So let's draw my picture. So first of all, I have a cylinder, x squared plus y squared is equal to 4. As I said, this is in the xy plane. This actually, let me draw in the negative sides of my axes here. All right. Okay, so in the xy plane, this is the circle of radius 4 centered at the origin. So maybe that's an okay way of drawing it. But this entire cylinder is the infinite cylinder. Looks like this, right? It goes up and down the z-axis, right? So here's my cylinder. Okay, so this is an infinite cylinder. Now it's bounded below by the xy plane. It's bounded above by this plane y plus z is equal to 4. So this plane is cutting kind of across like this. So this is kind of a bad picture, but what this does is it cuts out like this elliptical shape here off the top. And so the region D in question is this thing that I'm outlining here. So this plane cuts off this piece of my cylinder. So that's the top, right? Here's my top. The bottom is this region, right, inside my cylinder in the xy plane, but actually we know exactly what that region is, right? It's the region inside that circle in the xy plane, but that's just a circle of radius 4, right? So what is R? R is just our favorite closed disk of radius 4, right? So it is the set of all x, y in the plane such that x squared plus y squared is less than or equal to 14, so closed disk of radius 4. Okay. All right. So is there a nice way of putting this in polar coordinates? So in polar coordinates, how do I describe R? So in polar coordinates, R is described as, well, it is, I have R written as being bounded between what things? So it's all of the points inside a circle of radius 4. So my R, my distance from the origin, goes from 0 to a max of 4. And theta, it's the entire disk, right? It's not some portion of it. So theta goes from 0 to 2 pi. And so this is my description of r. So r is described thusly. So little r goes from 0 to 4, and theta goes from 0 to 2 pi. Okay. Now, of course, theta would go from 0 to pi if it was only like the top half, right? Theta would be between pi and 2 pi if it was the bottom half. If it was the right half, theta would go from, say, you could say theta goes from, well, okay. So if it was the right half, then we could basically rework this so that I could use negative theta values. So theta would go from minus pi over 2 to pi over 2, if you like. So anyway, this is that's just a quick refresher on how polar coordinates works here. All right, and so now I have a very nice and neat way of describing D in cylindrical coordinates. So I put that into practice here. So I'm going to rewrite this on a new sheet so that I can put it all on in one place. So reminder, here is my cylindrical coordinates formula. Okay, so see how this meshes with what I'm about to write here. So I was asked to evaluate the triple integral over D of square root of x squared plus y squared dv. Okay. Now, this is reminding you what I said D was. D is bounded, so in the z coordinate, it's bounded below by 0 and above by 4 minus y. R in polar coordinates is at the region bounded, so little r is bounded between 0 and 4, theta is bounded between 0 and 2 pi. So then this is the integral from 0 to 2 pi, the integral from 0 to 4. The inner integral is the integral from 0 to 4 minus y, but again, at this step, I am going to replace y here with what y is equal to in polar coordinates. So this is r sine theta. So this is the upper limit of integration here is 4 minus r sine theta. And then the thing that I'm integrating here, this integrand is the square root of x squared plus y squared. But what is that in polar coordinates or in cylindrical coordinates? Well, it's just r, right? And so this is r times, of course, this extra factor of r, dz dr d theta. Okay, so now I can actually compute this thing. So first of all, I have an r squared here that doesn't depend on z. So the integral of r squared dz is just r squared z. So this is the integral from 0 to 2 pi, the integral from 0 to 4 of r squared z evaluated from 0 to 4 minus r sine theta dr d theta. Okay. Doing this evaluating at 0, I get 0, and so evaluating at 4 minus r sine theta, what do I get? I have the integral from 0 to 2 pi, the integral from 0 to 4 of r squared times 4 minus r sine theta dr d theta. I'm going to expand this and then do it term by term with respect to r. So this is the integral from 0 to 2 pi, the integral from 0 to 4 of 4r squared minus r cubed sine theta dr d theta. All I did was distribute this r squared here. Okay, and so integrating this term by term, the integral of 4r squared, what is that? So this is the integral from 0 to 2 pi. Doing this integral, I have, what's the integral of 4r squared here? This is 4/3 r cubed, right? So 4/3 r cubed minus, what's the integral of r cubed sine theta? Well, I'm treating sine theta as a constant here, so this is minus 1/4 r to the 4th sine theta, and I'm evaluating this entire expression from 0 to 4 d theta. Okay. So let's see what I have going on here. If I'm plugging in 4 here, I have... So plugging in 0 into each term, I get 0, so I only have to pay attention to plugging into the top thing. So I would have 4/3 times 4 cubed, so that's 4 to the 4 over 3, which is 256 over 3. So this is the integral from 0 to 2 pi of 256 over 3. Okay, minus 4 to the 4th times 1/4 is 4 to the 3rds, which is 64. So this is minus 64 sine theta d theta. And now I can integrate this term by term here. So integrating this, what do I get? I get 256 over 3 times theta. So 256 over 3 times theta. Integrating minus 64 sine theta is minus 64 cosine theta. So it's plus 64 cosine theta. And this is evaluated from 0 to 2 pi. Okay, so then plugging in 0, I get 0 here, but I get 64 in this term. And so this is, and then I get another 64 that I'm subtracting off. And so all I get is, so I get 64 minus 64 from plugging in 0 and 2 pi into this term. Plug in 0 here, I get 0. And so the only thing I get that's left over from all that is 256 over 3 times 2 pi. So this is 512 pi over 3. Okay. So that's an example of how one of these cylindrical coordinates integrals goes. All right. Now, I wanted to do another example that kind of showcases another way that cylindrical coordinates can come up where you're not actually asked specifically, again, to do cylindrical coordinates. So you are just supposed to figure out that that's what you're supposed to do. So what's that example look like? So suppose I just flat out give you a triple integral where I've already written down the limits of integration. So my example is evaluate the following triple integral. You already know the bounds. It is minus 2 to 2 on the outer integral. The next integral has bounds of minus square root of 4 minus x squared to plus square root of 4 minus x squared. Okay. And the inner integral is the integral from x squared plus y squared squared to 1. And the integrand is x squared, dz, dy, dx. Okay. Now, this is all that's said. Okay, so imagine you're on an exam and I just say evaluate blah. Evaluate this triple integral. That's it. Well, you could go ahead and start doing that. You could go ahead and start working on this problem. But I would advise you against that highly. So while you will definitely get, if you follow through and do everything correctly here, you will get the right answer. This is going to be really, really messy and nasty. Okay, and I've actually given this exact example on past exams to students, and there were some students that made it really hard on themselves and did it correctly the long way and wasted a ton of time doing it that way. But then there were also students that noticed, oh, this is actually really easy if I do it in cylindrical coordinates. So before you think that was an unfair example or that was an unfair problem to put on an exam, I had actually done that example for them in lecture already. So it was kind of one of those like, do you remember us doing this in lecture sort of problems. So here it is. What about this should make you think about using cylindrical coordinates? The key thing that should kind of tell you that you should use some other type of coordinates The first two integrals, what is that region R you're integrating over? Right? Well, it is a closed disk of radius 2, right? So you are integrating over, so the R in question coming from these two, right? So this R, what is that R? This R is our favorite closed disk of radius 2. In polar coordinates, what is this thing? In polar coordinates, this is really easy. It is little r bounded between 0 and 2, and theta bounded between 0 and 2 pi. Right? So in polar coordinates, this is easy. In rectangular coordinates, it looks like this, right? It's a lot nastier. Okay. So this is kind of the hint to say, oh, well, in polar coordinates, this becomes a lot nicer. And in fact, in polar coordinates, what does this expression become? X squared plus y squared is r squared. So this is just r squared squared, or r to the 4th. So this is much, much nicer in polar coordinates. Okay, and so that's what tells you should use cylindrical coordinates for this triple integral. All right, and so let's do that. So let's rewrite this using cylindrical coordinates. So use cylindrical coordinates. When we do that, I'm not going to rewrite this thing. If I do that, I have this equals what? Rewritten using cylindrical coordinates. This becomes the integral from 0 to 2 pi, the integral from 0 to 2, the integral from r squared squared, which is r to the 4th, to 1, of x squared, that becomes r cosine theta all squared, times r dz dr d theta. Okay, let's clean this up a little bit. So this is equal to the integral from 0 to 2 pi, the integral from 0 to 2, the integral from r to the 4th to 1 of r squared times r is r cubed cosine squared theta dz dr d theta. Okay, now what? Well, here I'm going to integrate with respect to z. There is no z showing up here, so this is easy. So this becomes the integral from 0 to 2 pi, the integral from 0 to 2. And doing this integral, I get r cubed cosine squared theta times z. Right, so this whole thing times z. The z is not in the argument for cosine. Okay, evaluated from r to the 4th to 1, right, dr d theta. Okay, so really the only evaluation that I'm doing here is plugging in this 1 here, right? So this becomes 1 plugged in for z here, minus r to the 4th times r cubed cosine squared. So what does this become? This becomes the integral from 0 to 2 pi, the integral from 0 to 2 of r cubed minus r to the 4th times r cubed, which is r to the 7th, times all that times cosine squared theta dr d theta. Okay. So now I need to do this integral term by term here. I only have to pay attention to this because they're multiplying cosine squared theta, which is constant with respect to r. And so doing that inner integral, I have the integral from 0 to 2 pi of 1/4 r to the 4th minus 1/8 r to the 8th, evaluated from 0 to 2 times cosine squared theta d theta. All right. So let's think here. Plugging in 0 into both of these, I get 0, so I only have to worry about this 2 term. So what do I get? I get 1/4 times 2 to the 4th. So that's 16 over 4. So that's 4. Right? Minus 1/8 times 2 to the 8th. that's really, so 8 is 2 cubed, so this is 2 to the 5th really, so that's 32. So this would be 4 minus 32, which is minus 28. So this would be minus 28 times the integral from 0 to 2 pi of cosine squared theta d theta. Well, how do I do that integral? I need to use power reduction, right? I got to use power reduction. So remember, this is one of the formulas you got to know. So that is equal to minus 28 times the integral from 0 to 2 pi of 1/2 plus 1/2 times cosine of 2 theta d theta. So now I can actually do this, right? So I can pull a 1/2 out, and so, or maybe not, maybe I'll just do this term by term here. So this is minus 28. Doing this integral, what do I get? I get 1/2 theta, right? So the integral of 1/2 d theta is 1/2 theta, plus 1/2 times the integral of cosine 2 theta d theta. I would need a 2 d theta there, so I need to introduce another 1/2 on the outside. So this is plus 1/4. This would be sine of 2 theta. Right? From that integration, this would all be evaluated from 0 to 2 pi. Now, evaluating at 0, both terms are 0. Evaluating at 2 pi, this term is 0. And so I only get 1/2 times 2 pi times minus 28. So I get minus 28 times 1/2 times 2 pi, or minus 28 pi. Okay. And so this was another example of where calculating in cylindrical coordinates might show up. Okay. Again, in this example, there was absolutely no mention directly of cylindrical coordinates, but I looked at the form of the example. I looked at what the region I was actually integrating over would look like, or at least that R in the plane, what that would look like, and determined that this would be much, much nicer if I expressed this in polar coordinates, right? So it'd be much nicer if I expressed this in polar coordinates, which meant for the triple integral using cylindrical coordinates, right? Okay. So that is the deal. Now, I think it's a good stopping point here to kind of separate this from what's going to come next in terms of spherical coordinates. So I think what I'll do is I will end the lecture here, and then in your next lecture, we will begin the discussion of spherical coordinates. So next lecture is spherical coordinates, which is yet another way of expressing a region in space. So it's another coordinate system that is different than cylindrical coordinates, and I kind of hinted about this during last lecture, where there was a type of coordinate system that would make certain things that cylindrical coordinates doesn't totally make nice a lot nicer. So it's called spherical coordinates, so you might guess what things are much nicer in spherical coordinates. I won't spoil the fun, but this is what I'll talk about next. And once we finish spherical coordinates, we will be on to general coordinate transformations. Okay, and once we do that, we will be almost done with chapter 14, ready to move on to what is the last chapter in the textbook, which is chapter 15, which is going to see a return of everything that we've done so far. Okay, so chapter 15 is going to kind of tie everything together. All right. So anyway, that's that. So next lecture, as I said, will be on spherical coordinates.